Hello and welcome to this Chauvin Arnoux webinar. In this webinar we're going to give you an introduction to measuring power quality and energy demand. My name's Kevin Smith, I'm Business Development and Marketing Manager here at Chauvin Arnoux, and I'm going to be your presenter during this session. So for those of you who aren't familiar with Chauvin Arnoux, we were founded in 1893 by Raphael Chauvin and René Arnoux. Chauvin Arnoux has played a major role in the history of test and measurement. The long and prestigious list of its inventions, such as the universal tester, the ancestor of the multimeter, or the current clamp, provide ample proof of this. In the 20th century, more than 350 patents and brands were registered by Chauvin Arnoux. So just to give you an idea of some of the stats down the side there, we've got an annual turnover in the order of 100 million euros. We've got 10 subsidiaries spread across the world, of which the UK subsidiary is one of those. About 900 employees, 7 production sites, 6 R&D departments worldwide, and we're quite proud to say that we spend about 11% of our revenue on R&D, which shows we really are a sort of forward-looking company, continually coming out with new products. So in this webinar, there's a few things that we need to talk through before we get started. So the first one is testing 1 2 3. Just make sure that you can actually hear me, you can see the screen and all those sort of things. And if you wouldn't mind just typing into the chat box just to confirm that you can actually see and hear everything that's going on. That just gives us a little bit of confidence that everything's working as it should be. If there is any problems, obviously, just have a look at your computer settings. Usually it's down to something like the audio settings or something like that. And you might just need to leave the webinar and re-enter again or restart your PC to actually to get everything up and running as it is. So the duration is approximately 1 hour. I say approximately, it may run a little bit over that. And also at the end, we have a live Q&A session. So the live Q&A session, what we do is we open up the microphones and we take questions from the delegates who've been watching the webinar, and we carry on and we answer those until all of those have been answered. So that will stay on at the end of the webinar until we've answered all of the questions that are there. Now, during the webinar, you can use the chat box for your questions. So if you have a look on the go-to toolbar, you'll see that there's a chat box, and you can just type in there your questions, and we've got a team of people on standby, myself included, to answer those questions as we go through. And obviously the best of those, or if there's more complicated ones, we'll hold till the end as well, and then we'll address those during the live Q&A. Another thing to be aware of, remember to download the presentation handouts. There is a PDF version of the presentation slides available. Again, if you go to the go-to toolbar, you should see a handout section in there, and you can download those before you leave the session, so just make sure you get your copy of those. After the session, there will be a certificate sent out. There'll be an email thanking you for attending, and with that there'll be a certificate of attendance sent out after the session. And also, once we've finished, we've got 2 showings of this. So once we've finished all of the showings of the video, we'll also get a video uploaded onto our media website, www.cauk.tv. So that'll be on maybe a week or something like that after we've done the sessions, and we'll get that up on there, so you can check that out if you want to watch it again. So what are we going to cover in this session? So we've called it an introduction to measuring power quality and energy demand, and we've split that down into a few parts. So the first bit is, what is power quality and energy demand? Then we'll go on to look at, why is it important to you? What properties can we actually measure? What are we actually measuring when we talk about measuring power quality, measuring energy demand? And what's the difference between actual live measurements that maybe we're a bit more used to, taking those measurements, live readings at the time, or logging these things over a period of time, and why might we want to measure things over a longer period of time? So the intention of this session is it's very much a low-level introduction, just really to get you into the subject of power quality and energy measurements, and just understand the basic terms. And then obviously over the next few sessions we'll build up and we can get into a bit more detail on these specific topics. And we've also, within Chauvin Arnoux, particularly on our CAUK.tv website, We've actually got a lot more content in there that you can look into if you want more detail on these things as well. So now let's have a look at what is power quality and energy measurement. So firstly, let's start by clarifying the terms used above. Power quality is often the blanket term used for the type of measurements we are discussing in this webinar series. But the name can be misleading. The word power, for example, can have multiple meanings. So power could be the actual electrical term power that's measured in watts. So sometimes people get confused between measuring power and measuring power quality. And in this context, we're really talking about power as the electrical system, a power supply, electrical power. We're not talking about the unit power. We're talking about really it is a power supply, a source of energy, really, in that context. So in our context, power can be taken to mean the electrical properties in a given circuit, really. That's what we're talking about. We're talking about the electrical properties that a particular circuit or supply has. Now, the other term, quality. Quality is a term that can also be misleading, but is essentially defined as being fit for purpose. So anybody who's done, quality management courses and things like this, they always talk about, what is good quality. And people always think, it's the premium, it's right at the top end, it's really good quality. But actually, quality is generally defined as how well does it meet its specification? How well does it do its job? How well is it fit for purpose? So really, what we're doing is we're simply measuring if an electrical circuit is behaving as specified. So when we talk about power quality, what we're actually doing is we're saying we've got this electrical installation, we've got this electrical circuit, or we've got this supply. Is it performing as specified? Now, if we look at energy efficiency is closely aligned with power quality measurement, because generally a lot of the times we're using power quality test instruments and we do very similar measurements to power quality when we're looking at energy efficiency. But energy efficiency concentrates on quantifying electrical energy usage and identifying potential savings. And energy efficiency measurement is a fast-growing part of the test and measurement industry. As energy prices continue to rise and all these sort of things, historically maybe people were more worried about the operation of circuits and getting them to operate effectively and getting them to work, whereas now we're using the same tools but we're looking at it in a slightly different way. We're looking, what is the energy usage? Where can we identify savings? And sometimes power quality issues can also identify areas that we could improve and save money at the same time. So they are closely related, hence why we're talking about them all together. But generally, energy efficiency is a sort of branch of power quality analysis. And obviously, it's something we're going to talk about more today. So why is power quality and energy efficiency important to you? So let's first look at power quality. So poor power quality causes many problems. And a lot of problems that you just don't know, or you don't know what's happening. Often it's that niggling thing that you don't really, there's something going on, but I'm not quite sure. A lot of times that can be put down to a power quality problem. So we can have disruption to the operation of equipment. We can have premature failure of equipment. So equipment's failing more often than you'd think. And you think, why is this equipment always failing? A lot of times it can be down to a power quality issue. Overheating and increased fire risk. Increased project costs through over-specification. So a lot of times people actually say, well, I don't really know about my harmonics, I don't really know about this, so I'm going to use a bigger cable, I'm going to use a bigger transformer, I'm going to use a chunkier motor, I'm going to use a bigger drive, or I'm going to specify a bigger supply when I install this installation, because I don't really know, I'm not sure, so I'm just going to chuck money at it. Really, I'm just going to overspec it, and I'm sure it'll be absolutely fine. Increased call outs and fault finding costs. A lot of times all these sort of nuisance tripping of items or things just resetting for no reason, and a lot of that can be down to power quality, and we can use the power quality techniques to actually improve the way we do that and minimize the downtime. Obviously, increased maintenance costs. Again, if we're getting things overheating, we're getting things wearing out quicker, the maintenance costs go up. And as I've put on there, many more. The more you get into power quality, the more you'll see the benefits and the advantages and the things that you'll actually oh, I didn't realise that was caused by that issue. And again, the more you get into it, the more you can refine and the more you can improve over time. Now, talking about energy demand. Now, energy is, very important. All businesses need energy to operate, but over time, energy demand is predicted to rise massively. So if you have a look at here, the National Grid figures for the next sort of 20, 30 years, there's various scenarios, but in all scenarios, they're looking that demand will generally go up. And if electric vehicles come online and all these sort of things, it's just going to go up and up and up energy demand. So it just becomes more and more important for us to understand what our energy demand is and look for ways to minimize it. Across the country, minimizing energy demand and trying to be more energy efficient is something that often gets overlooked, really, but we can't just keep building power stations. We can't just keep trying to get more and more generation capacity in there, when actually the real issue is the waste and the inefficiency that's within these systems. So again, the whole energy demand side of things, the whole energy analysis is becoming more and more important and will over time. Now, this is the figures that I've pulled up from the utility helpline, but this actually just puts in context again the rising gas and electricity prices. You can see over the last 12 months there, the wholesale electricity prices just continue to go up and up and up and up and up to levels that we haven't seen in, ever probably from that side of things. So again, in businesses, this is just getting more and more important. The return on investment of getting involved with power quality and with energy analysis is just getting that much better, really. It's something that businesses can't do without almost, and over time, this will become a bigger and bigger part of all electricians' jobs, actually getting more involved with this and identifying those savings and really fine-tuning that electrical installation to be as efficient as possible. Now, also, we're aware we've got the COP26 coming up, the UN's summit on climate change that's coming up as I record this. It's probably about a week away or so. So again, we're getting more focus on environmental issues. We've got targets to get to net zero and zero emissions and things like this by 2050. So again, there's this greater emphasis on environmental issues, and energy efficiency and electrical installations is just becoming more and more and more important. So let's take a look at what properties we can measure. Now, often people get confused with power quality measurement, and they assume that they hear all these terms like harmonics and power factor and things like that, and they assume that there's a different test instrument and all these connections to measure different things. And actually, it's a lot more simple than that. It's very, very simple. What we're actually measuring when we measure power quality is voltage, either between live conductors or to earth, and current, either at the incoming supply or for an individual circuit, or maybe just even for an individual piece of equipment. So from the voltage and the current measurements, we plot these against another important factor, which is time. And then from those, all of the other values we talk about can be derived. So actually, the test connections, when we talk about power quality, are very simple. We're making a voltage connection, as you can see on the top left there, and at the bottom, generally when we take a current measurement, we're using an indirect method, using a Rogowski coil or a current clamp. So we're not even running the current through the test instrument, we're using a clamp to actually do that. So we make the test connections. Obviously, these things are plotted against time, and then using some very clever test techniques and some very clever maths within the instruments, from those we then get all of the things like power factor and harmonics that we will talk about later on. So when you're concentrating on power quality, don't worry about the complexity of all these complex measurements, because actually the measurements are just voltage and current, and it's as simple as that. Now, I wanted to start off here just talking about, the standard electricity supply in the UK. And everybody has this picture in their mind that we get an alternating current waveform, 50 hertz, standard 230 volts, AC waveform, and it looks like a perfect sine wave, just like we've got on the diagram there, and everything's great. And as you'll see in reality, it can be quite different. Now, in the UK, we've got something called the ESQCR, the Electricity Safety, Quality and Continuity Regulations. And these lay out in very basic terms the standard for the electricity supply. So it should be 50 hertz plus or minus 1%. It should be 230 volts AC RMS plus 10% minus 6%. And for those of you who take a high voltage supply directly from the grid, from the suppliers, if it's less than 132 kilovolts, it should be that plus or minus 6%. And if it's over 132 kilovolts, it's allowed to be plus or minus 10%. And that's what's laid out in the ESQCR, the Electricity Safety, Quality and Continuity Regulations. Now, many of you will be experienced with or will have three-phase installations, and the three-phase installations are separated equally to 120 degrees. So when we talk about a three-phase installation, we've got sort of three lots of that 230 volt waveform separated by 120 degrees. Now, I mentioned earlier about the EN standard 50160, and beyond the simple requirements of the ESQCR, which are very basic, we do have the requirements of EN 50160. And this is the standard used by the power quality industry to fully define power quality and the test equipment used. So when you get more into this and you get more into the minutiae of it and actually understanding the individual terms and the individual standards in there, if you get a copy of EN 50160 and have a look at the details in there, everything is defined to minute detail, and that's really when you start getting more into power quality, you'll see the details of what you need to know are really in that standard, and that standard is really the basis for all power quality measurement. So let's have a look at some of the anomalies, some of the things we might be looking for when we're doing power quality assessments. So I talked about this perfect sine wave. We were saying about that. We have this perfect vision of a sine wave, and actually quite often that changes. So we get these things called voltage sags and voltage swells. So a voltage sag or swell is a short duration reduction or increase in the RMS voltage, often caused by changes in loading, for example, switching on or off large motors. So again, you can imagine that we've got the voltage, piece of equipment switched on, suddenly creating a big load. That big load, increases the current, and we get a bit of a dip in voltage until it sort of returns back to normal. So again, we'd get a sag in there. Now that event might not really matter, or it could be enough that it's enough of a dip that it affects the operation of another piece of equipment, maybe causing a contactor to drop out or a piece of IT equipment to reset or something like that. So again, all of these factors happen. It's just a question of how much do they happen, and then when we're quantifying these, often we're trying to diagnose an actual fault, and it could be that we've got a voltage sag or a voltage swell going on, and obviously we can identify that through power quality measurement. Another thing that we're looking for, and that can cause problem again with equipment, potentially damage equipment or cause strange operations, is these things that we call transients. And transients are very, very fast events. So they happen just for, a very, very short period of time. But they can, have very high magnitude. They could be in the kilovolts. So you get these little spikes on the waveform that actually just happen. And a lot of time this is due to switching on and off capacitive or inductive loads. It could be due to arcing. You can imagine maybe using welding equipment, or there's an arc in a switch, maybe a switching contact or a relay contact is become corroded, and you're actually getting that little bit of arcing in there that could be causing this. Or even environmental effects such as local lightning strikes can cause this sort of thing to happen. So again, you know, one of the things we are looking for when we do power quality measurement is transients, but these are very, very fast events. So we really need to have our instruments set up to be able to capture these things, because they do happen, you know, in a sort of, you know, sometimes in the case of microseconds. So we do need to really, really be set up to capture these when they happen. Electromagnetic interference, you can see quite a woolly looking sine wave there. And a lot of times this is a disturbance actually generated by an external high frequency source that affects the electrical circuit either by electromagnetic induction, electrostatic coupling, or maybe even conduction. So you can imagine if you've got, say, a radio transmitter and it's very close to your power supply, you can have that electromagnetic radiation, electromagnetic induction going on, and that's being picked up by the supply cables, and you actually get this sort of, you know, high frequency waveform superimposed over the top of your sine wave, and that obviously can cause all sorts of problems. So it's you know, another form of interference, really, this electromagnetic interference, and again, you know, it's something that we can pick up when we're doing these power quality measurements. Now, something that is quite common actually in a lot of installations, in fact I would probably say most installations, if you've got a three-phase system, that there is some sort of imbalance, that you haven't actually got identical loading on each of the three phases. Now this could be because you've got a single phase load, so you need quite a high current single phase load in there. It could be because you haven't actually balanced your loads correctly across the phases, so when you've installed the distribution board, you know, more equipment has been put onto phase L1 than the others. And what that does is it means that there's actually an increased current loading on a particular phase, which can then affect the voltage, because, you know, you get more volts drop and things like that present. And then you're actually seeing that these voltages and currents are out of balance. And what that means is that if you are then using them with three-phase loads, like a three-phase motor, for example, then it's not seeing equal, energy across all of that rotation, across all of the operation, and that again can affect the life of the motors. It can affect bearings, it can affect all sorts of things. So again, you know, loading and load imbalance is something that we would be looking for when we're actually carrying out power quality assessments. And it's something that is very, very common. In fact, I would say it's in most three-phase installations to a certain degree. You probably wouldn't, you know, it may be, you know, sort of below the tolerance of what would be a problem, but it is something that happens quite a bit. You know, there is generally some sort of difference in loading across the phases. And in extreme cases, obviously, that can cause a problem. Inrush currents or starting currents, yes. So when we actually start up a piece of equipment and they're first switched on, there's an increased current demand, which then reduces to a steady state. This is known as the inrush current. So typical examples include motor starting, turning on heating elements, some lighting we turn on. So for a short period of time, we get this increased current. So you can imagine with a motor, when we first start it and it's in a static state, there's a higher current to get it up to speed. And then once it gets up to speed, the current drops down and it operates. Now, the problem with this is that we need to make sure that, for example, the circuit breakers that we've used don't operate because they see this high starting current. But also, we don't want circuit breakers that are actually set way, way, way too high for the normal operating current, because under normal operating conditions, we want it to still detect a fault. So again, understanding these inrush currents, understanding where they come from, and then obviously designing the protected devices, the conductors, the switchgear, and, you know, motor drives, all those sort of things to account for this is very, very important. So in power quality, sometimes we can actually, you know, set up the instruments to look particularly at these inrush currents to be able to quantify them, and then we can obviously design the installation to allow for those characteristics, because it isn't a fault, it's a characteristic of that particular load. But obviously we need to be aware and we need to design the installation to allow for that. And if that hasn't been done, again, sometimes this can be where you're chasing faults and you're finding what's gone on, and then obviously you can alter and you can redesign circuits to operate correctly. Now, another property that we talk about, I mentioned briefly when I was saying we can get confused between this and power quality, is the actual electrical term power. So power is really defined in basic terms as the ability to do work. It's the sort of oomph that the circuit's got. And in a purely resistive circuit, the power to do work is calculated by multiplying together the voltage and the current. So P equals V times I. When you've got voltage and you've got current together, that gives you the power. That's the ability to do work. So you can see from the diagram that in this case, all three properties are said to be in phase. So when we've got a resistive load, the voltage and the current happen at the same time. So as the voltage increases, the current increases, and because the power is just the result of both of those two, everything's in phase. So you can see from that diagram that we've got everything there in phase, and it's all happening at the same time. Everything's all predictable, and it's nice and easy. Now, the problem is that power in the real world doesn't quite work like that. And in reality, circuits always have some inductive elements, such as motor windings, and some capacitive elements, such as, say, a starting capacitor on a motor. So, because in the real world, all circuits will have some degree of inductance and capacitance, these elements affect the current flow in the circuit and cause it to be out of phase with the voltage. So they sort of have an equal and opposite effect, inductance and capacitance. But the combined effect, usually they don't fully balance out, and we'll end up with either the current or the voltage leading or lagging each other. And then as a result of that, obviously the power then is also out of phase too. So we've got various types of power, or various definitions that we use for power. And the first one I'm going to talk about is apparent power. And apparent power, we don't use the symbol P. For apparent power, we use the symbol S. And the unit of apparent power is VA, volt amps. So when current and voltage are out of phase, the amount of power consumed can be deceptive, as they do not peak at the same time. So if you imagine what I'm saying there, we're actually measuring, so if we measure the voltage and we say, yeah, we've got 230 volts, and we measure the current and we say, yep, we've got 10 amps. And we would imagine you multiply those two together and you get the power. But they're not happening at the same time. So when the voltage is going to 230 volts, that's not the same time as the current is actually at 10 amps. These things happen at different times. So the resultant power, or the apparent power, actually can be confusing, because we assume that we just multiply the current times the voltage, the V times the A, and we get this apparent power, this higher power. But in real life, the real power that we get is actually lower than that, because they're not happening at the same time. So if you were to measure the voltage and the currents, then multiply them together, you would get an incorrectly high value. And that's what we call the apparent power. So if we just measure them separately, multiply them together, it appears that we've got more power than we actually have, because they're not happening at the same time as each other. Now, what we're interested in is we're interested in real power, the actual power that we do have. So the relationship between apparent power and real power can be shown in a triangle, where the angle theta is the phase difference. So we said the voltage and current are out of phase. If we plot the phase difference on here, we can actually plot it in the form of a triangle, which shows us what's going on. So what you can see there is that the apparent power, V times I, is longer, appears to be longer than the actual power. If we correct it using the phase angle, the real power, P, is actually V times I, but then, a bit of trigonometry, the cosine of theta times by the cosine of theta, and that actually then gives us what we call the real power, the true power, because we've compensated for that difference in phase. So by the magic of trigonometry, cos phi is the ratio of apparent power to real power, and we call this the power factor. So you'll hear endlessly people talking about power factor, and this is what it is. The power factor is the ratio of the apparent power, what we think we've got, to the real power, what we actually have got. So we also talk about this thing, or we mention this thing, reactive power, and we give that the symbol Q, and that has a unit VAR, volts amps reactive. So in a purely resistive circuit, or one that has a balance of inductance and capacitance, apparent power and real power are the same, and the power factor is perfect, or 1. So the best power factor we can ever get is 1, the ratio of 1 to 1. There's no reactive power, and the apparent power and the real power are actually aligned, and we've got no waste, for want of a better term. But when inductance and capacitance are out of balance, we get what we call reactive power. That's the the difference between the two. That's the power that's going in that reactance. It's going in the non-resistive part of the load. And this is generally seen as waste. I know some people sort of argue, the term waste is wrong. It's just a different type of power and that sort of thing. But realistically, it's not doing, in most cases, it's not doing a useful job. It's the real power that we want, the real power that's there. And you'll see on the right-hand side, quite often this analogy is used here with a pint of beer, where the reactive power is the head on the beer, the real power is the actual beer that you get to drink, and the apparent power is the whole lot. So you're thinking that you're getting a full glass of beer, but actually, because of the head you're getting on there, you're actually not getting the full pint, shall we say there. So that's quite often used as a sort of nice analogy for it. So power factor correction. So remember, power factor is the ratio between the apparent power and the real power. So your electricity bill is likely to be based on the apparent power. So you're paying for what it looks like the installation is using, not necessarily what it is using. So you will pay more if you have bad power factor. So it's in your interest, and particularly if you're a high current user, you're a high demand user, to actually reduce that power factor. So in many large installations, it is normal that bad power factor is caused by too many inductive loads, such as motors. So most installations, we're not likely to have too many capacitive loads. It's usually inductive loads, motors, transformers, all that sort of thing that we're likely to have in the installation. So normally you've got too much inductance. In these cases, power factor capacitors can be added to balance the circuit and reduce the power factor. So if we've got too much inductance, we add in capacitance, and that brings it back into alignment. They cancel each other out, and we reduce the power factor. We reduce the phase angle. We increase the power factor, trying to get it as close to 1 as possible. And that actually gives us a more efficient electrical installation. There's less waste there, and it'll also reduce our electricity bills at the same time. Now, moving on to talk about these things called nonlinear loads. Nowadays, many modern loads are not constant throughout the whole supply curve. So throughout the whole sine wave, they're not a constant load. They switch on and off. They change their demand, not over long periods of time, but actually very short periods of time throughout the waveform. These are classified as non-linear loads and create very complex waveforms, as you can see on the right hand side there. So that's a sort of typical waveform we'd see for an electronic power supply. It's drawing current at certain parts throughout the waveform, not throughout the whole curve. Typical examples include electronic power supplies, fluorescent lighting, rectifiers, and variable speed motor drives. So again, we're getting more and more of these in electrical installations nowadays. These complex waveforms can cause a wide variety of issues within the installation, especially if they combine. So you can imagine if we've got, one little power supply, it's not so much of a difficulty, but if we've got loads of them in an office, if we've got loads of motor drives, say in a factory, again, the combined effect of these can have a big impact on the waveforms. So a common example being overheating of electrical distribution equipment, cables, transformers, motors, standby generators, and other components. So again, most of the distribution equipment isn't designed to deal with these sort of quick switching on, switching off, high frequency events that are going on. They're designed for sort of steady, normal linear loads. So again, when we're introducing nonlinear loads into that and introducing what I'll talk about in a moment as a result of that, harmonics, again, that can have detrimental effects on the electrical installation. So to analyse complex waveforms, we can use a mathematical technique called Fourier Analysis. So Fourier Analysis, this breaks down any waveform into its fundamental and harmonic components, which can then be analysed individually. So this is quite a clever technique, and the technique means that basically we can break down any waveform, any shape waveform. So you can see on the top right there, we've got a waveform that looks almost like a square wave, but that's actually made of multiples of other frequency waveforms added together. Now, what we can do is we can sort of do it the other way around. If we want to know, well, what's causing this waveform not to be a sine wave? What's causing this waveform to look distorted? We use Fourier Analysis, and Fourier Analysis then allows us to plot, as you can see there, the spectrum of these harmonics on a graph. So what we can see is that the distortion is made up of the fundamental frequency, but also it's made up of these various harmonic components. And by looking at these harmonic components, quite often we can use that to diagnose what might be causing it. Because through experience, we know that if there's a lot of a specific harmonic in there, that is likely to be caused by a particular type of circuit or a particular type of load. So then we can go looking at that and say, actually, yeah, that's where the problem is. That's what's been causing it. So we're taking a waveform that's been distorted by these nonlinear loads, and we're using Fourier Analysis to plot it in a format that allows us to better diagnose what's going on. So harmonics are generally referred to as a multiple of the fundamental frequency. So if we're talking about the third harmonic is 3 times the fundamental, so it's 3 times 50 hertz or 150 hertz. So we're saying we're actually seeing, if we're saying we've got third harmonic, we're actually seeing frequencies in there of 150 hertz at 3 times the fundamental. Analysis of harmonics, diagnosing problems and specifying mitigation measures, is an interesting and growing part of the power quality measurement. It's an art form. It really is an art form, and it takes a lot of time and a lot of experience to actually be able to read what's going on with harmonics and understand what's meant to be there, what's not meant to be there, what we can do something about, what's having the, what effect. So it really is almost a sub-branch of power quality measurements, understanding harmonics, and it's a really interesting area, and it's something that more people are understanding, more people are getting into, but it does take a lot of time and a lot of experience to actually be able to read harmonics correctly. Now, a simple way of specifying or measuring, quantifying, shall we say, harmonics is using this thing called total harmonic distortion, or THD. So what THD does is it basically is a simple measurement that quantifies the amount of current or voltage harmonics present in a system. This value is a ratio of the current or voltage measured in the sum of all of the harmonics versus that measured at the fundamental. And this is often displayed as a percentage. So what we're saying is we've got a value of, say, voltage for the fundamental at 50 hertz. We add up all of the voltages at all of the other harmonics, and then we display it as a percentage. So what percentage is harmonic distortion versus the fundamental? And you can see on the graph on the right here, or the display on the right, we're actually measuring current there. So we're talking about current harmonics, and you can see there that we've got quite high 3rd, 5th, 7th, 9th harmonic content in there, and the actual THD is measured there at 36.5%. So that's quite a lot compared to the fundamental. Obviously, generally, if there was no harmonics, we want everything to be in the fundamental, no harmonics present, and that, is a perfect, perfect sine wave again, getting back to where we were. But this is a very useful measurement, THD. It's a quick measurement. You take the THD, and then obviously if you looked at it and said, oh God, we've got a lot of harmonics present here, that's when you'd start to do the Fourier analysis. You'd start to look into it in more detail. Right, where are they coming from? What are they? Why have we got them? What's the effect? So THD is almost your sort of starting point measurement. If your THD is okay, you really know you haven't got a harmonic problem. Whereas if your THD is high, then obviously then you would start to go into that a lot more and start to dive into it. So THD is almost the starting point for harmonic analysis, and then you would really start to diagnose into that using the waveforms and things like that afterwards. Now, we've talked a lot about power quality and the power quality measurements that come up. Now let's just have a little bit of a better look at energy measurement. So measuring energy usage and, importantly, cost. So electrical energy is generally measured in kilowatt hours. So a kilowatt is 1,000 watts, obviously multiplied by the time. So generally we define sort of energy as power times time. It's the power that you're going to use. So if you were using 1 kilowatt, so you've got a 1 kilowatt radiator and you're using that for an hour, that would be, the energy would be 1 kilowatt hour. You use 1 kilowatt for an hour, that's a kilowatt hour. And that's generally what we refer to in the UK as a unit of electricity. That's normally what your electricity meter measures in units, is kilowatt hours. So the average cost for standard electricity in the UK in 2020 was about 17.2 pence per kilowatt hour, according to the Department for Business, Energy and Industrial Strategy. So you can look at that and you can say, right, so a kilowatt hour, if I'm using 1 kilowatt for 1 hour, that's roughly cost me, depending on what you're paying for your electric, 17.2 pence per kilowatt hour. But you could see that the actual wholesale prices I showed you earlier in the webinar were going up massively. So we can expect those prices to actually climb. But what we can do using this is, obviously we could measure energy using our energy loggers or our power quality meters, and then we can apply, we know how many kilowatt hours we've used. We can actually then apply the unit price, and we can get that into pounds, shillings and pence. So we know what the electrical installation, or what parts of the electrical installation, is actually costing to run. And that's an important part of energy efficiency and actually, putting those business cases together for improvements. Now, for measuring energy usage, we actually have another value, another important property that needs to be thought about a lot more now. I talked about COP26 and zero carbon by 2050. So we actually have this local equivalent CO2 emissions per kilowatt hour value. It's what they call intensity. They actually call it an intensity figure for some strange reason. So this is equivalent CO2 per kilowatt hour. Now, this does depend very much on where you're getting your electricity from and where the grid is getting its electricity from. So there's actually live data on the internet, but it varies between sort of 50 grams up to about 200 grams of CO2 per kilowatt hour currently in the UK. It depends how much wind there is, how much, when they switch on a coal-fired power station or turn it off, or, whether they're getting some from another country or whatever. So the balance is constantly moving up and down, and they do plot the maximum and minimums. But what this allows you to do is, we said you can actually take your kilowatt hour figure and turn it into pounds, shillings and pence. What you can actually do with this is, obviously you can take your kilowatt hour figure and turn it into your carbon footprint. How much carbon have you used this year? How much carbon have you used, this week, or has this machine used? And that can actually be used for your business to calculate your business's carbon footprint, or for a customer. But also it can be used for carbon offsetting. So a lot of businesses have decided to go zero carbon. And I was recently talking to somebody about the Commonwealth Games coming up next year. In Birmingham, and the Commonwealth Games is actually going to be the first zero carbon games. So again, they're very interested in measuring, the carbon footprint. I'm very interested in looking at carbon offsetting and things to make this, event zero carbon. And it is something that more businesses are interested in now. If they're building a factory, can we make this a zero carbon factory? If we're actually producing a product, can it be zero carbon? If we're doing a festival, say, can that festival be zero carbon? So measuring these things is very important, and actually it's one of the things that's actually becoming more prevalent now as people pay more attention to these environmental issues. So when we're measuring energy, we're not just measuring kilowatt hours. We can obviously plot that into money, and we can plot that into tons of CO2, or in this case grams of CO2 that we're actually using, and get those real world figures. And that's what customers are becoming more and more interested in as we go. And in this last section, I just want to talk to you about the difference between live measurement versus logging. So when we talk about measurement, we talk about things like the data sampling rate and also the sampling period. So while many power quality measurements can be viewed live, either on the front of the tester or using the software in live view, in most cases, events either can be too fast to observe. So you imagine something like a transient, no way we'd see it, or happen at random times when you're not looking. So again, you're trying to find a fault. There's this dip that's happening every so often. The chance of you actually watching the screen on the meter when that dip occurs is, virtually zero. So this is where the right test equipment comes into its own. So we want to set up the test equipment with the right sampling rate, the right sampling period to actually capture the events we're looking for. So we must select and set up test equipment to capture the events we're looking for. Short-term events like transients or inrush currents require high sampling rates to fully capture the detail of these events. Longer-term events like power outages don't require such detail. In many cases, we're just looking for a maximum or minimum value, so longer aggregation periods are more than acceptable and keep file sizes down. In all cases, the sampling period must be long enough to capture fully any variations in what we are measuring. For example, if you're looking to measure simple maximum current demand for a small business, it would be advisable to run the logging session for at least a week to capture any variations in working patterns, although longer periods may be required if specific activities only occur on a monthly basis. So it's important really to talk to the customer, to understand what you're measuring, to understand any variations, and then you can allow for that within your measurements. So we're now at the end of the webinar, and I want to summarise what we've covered. So we're going to give you an introduction to measuring power quality and energy demand, and we looked at what is power quality and energy demand. So we looked at the terms, what's meant by power quality, and what are we looking for when we are measuring energy. We covered why is it important to you, because obviously it can cause a lot of disruption. Bad power quality can cause a lot of disruption within your electrical installation, but also energy now is becoming more and more prevalent, and actually quantifying energy, looking for energy savings is a big part, or going to be a growing part of what we do. We looked in detail at all of the properties that we could measure, and we said that they were all derived from voltage, current and time, but there's a lot of different measurements in there that we can look at, and obviously we can talk more about that in coming events. And we just briefly finished up there with a little chat about the fact that we can do live measurements or we can do logging over a period of time, and generally when we're looking at power quality and energy efficiency, we're probably going towards logging over a period of time to make sure we're capturing those events. So thank you for attending. There's a few things I just want to go through with you before you go. So remember to download the presentation handouts. Go to the go-to toolbar and look for the handouts section. Make sure you download those before you leave. A certificate will be sent to you after the session, so you get an automatically generated certificate to say you've attended the event. And we will be running the part 2 in probably, I don't know, a couple of 3 weeks time, something like that. It'll be on your booking there, depending on when you're watching this. So in part 2, we're going to have a look at the 18th edition wiring regs, specifically to see what they say about power quality and energy efficiency. So that's going to be quite an interesting delve into the wiring regs, because there is a lot in there about power quality and energy efficiency, and a lot of times people don't realise these requirements are actually in the wiring regs. So that's going to be an interesting one. Now, for more information on the subject, if you want to do a bit of reading up to follow up on what we've talked about or in preparation for future sessions, if you go to our website, www.cauk.tv, that's our website where we put all of our articles. We've got loads and loads of over 30 odd articles on there about power quality and energy efficiency. We've got videos, we've got all sorts of stuff on there, so definitely worth checking that out. Also, just to mention, if you look us up on social media as well, because that's a place where we also share more information. So now what we're going to do is we're actually going to hand over to the live Q&A. So if you hadn't realised, this is a recorded version of me. So I'm now going to hand over to the live version of me, and I've got my colleague with me as well, and we're going to go through the Q&A. So if you've got any questions left, please type them into the chat box now, and we'll answer them shortly. Thanks for attending.